Okay, good morning. And today I'm going to do something a little different in the sense that I want to cover the circuits that we're going to use in the lab next week, which is the rectifiers and clippers and clampers. We won't have time to get into the clippers and clampers, but I want to discuss rectifiers. And what we'll do is we'll do a low-level explanation, meaning qualitative explanation of how a circuit works using the ideal diode model. We won't go into the mathematical equations, not just yet, because I want students to understand what the circuits are doing first, and then we'll go into the mathematical equations and derivations. Okay. Also, at this time, I would also like to recommend to students that we learn about atoms, electrons, and holes, movement of charge carriers, semiconductor physics in chapters 2, and a little bit at the beginning of this chapter also. But I would like to recommend to students at this point to zoom out a little bit, take kind of like a 10,000-foot overview, and think of the diode as a component that you're using in building the circuit, right? So put a pin on the movement of charge carriers and how electrons are flowing or how holes are flowing for now. Understand what the circuit is doing first, and then we can zoom back in and have a further in-depth understanding. Because if we don't understand how the circuit is working and we don't understand how the diode is actually being used, then there's no point in us trying to understand anything further in the terms of like device physics and stuff. Okay, so think of the diode as a building block, and the ideal diode model, diode is either on or it's off. Okay, and so I will use that model, explain how the circuits are working, and the next week we'll look at the equations and all the other quantitative stuff. Okay, so here's the notebook. And the homework, the first problem specifically, requires VD0. And so VD0 is simply the diode voltage minus the thermal voltage VT. This is, and it was like an assumption on my part, but I shouldn't have assumed. So this is there in the assigned reading, which is section 3.10, 3.10. And these equations are there. And of course, VT is KT over Q. K is the Boltzmann's constant. T is the temperature in Kelvin. Q is 1 unit charge. And then diode resistance RD is simply VT over ID, diode current. So this is section 310, and it's either 0.2 or 0.3, I believe. 0.2, I believe, the iterative model. Okay. It's basically trying to find a solution for the mathematical equations. And so you would need these equations to solve for that first problem in the homework. Okay. All right, let's get to diode rectifiers. Multiple diodes is also something we will do next week. Okay, for this diode, yes. So here, sure, it is the resistance of the diode, yes. So, diode characteristics are nonlinear, right? But if we zoom into any single portion, we can treat a small piece or a small portion of that characteristic as linear, right? Hence the piecewise linear. So the diode Q point or the operating point could lie anywhere along this characteristic. So if you wish to find a solution to that Q point, to solution for the Q point, using the mathematical model, we have the transcendental equation that we cannot solve. So we try to find a starting point And let's say this is the Q point, for instance. The Q point, of course, could lie anywhere along the line. We don't know where it is. That is what we're trying to find out. So we treat that portion of the characteristic, meaning at the Q point, as linear. And we draw a line that intersects the x-axis right there. Again, the Q point is unknown. That is the goal, to find the position of the Q point, right? So if we treat it as linear, and we say that the Q point linear line is intersecting somewhere the x-axis, that point is VD. Okay, that point is VDO or VD0. Right there, intersection with the x-axis. And then the slope of that linear line is known as conductance, I over V. Right, the line. This is the characteristic. You have I here, and you have V here. Right. So the slope of this line is I over V. Diode conductance, and the diode resistance is the reciprocal of that conductance. And in mathematical terms, right here, this is R, not V. RD can be given as VT or the diode current ID. Okay. At the Q point, that's the value. At the Q point. And then we can take this VD0 and plug it into our transcendental equation, and you can find the solution. Okay. So again, I would strongly suggest, well, I would suggest, I keep using the word strongly, but I would suggest students do keep up with the assigned reading. So the assigned readings do have material that cannot always be covered in class. That is typically the point of homework, right? To extend the student's learning. Something that cannot always be covered in the class. I mean, you learn the concepts in class, and then you learn a lot of it outside of class also. Okay. Does that answer your question, right? Okay. Constant voltage drop, multiple diodes. Again, we'll do this next week. But again, the goal for me today is to at least get the rectifier circuits done, because in the lab next week, especially students who are in my Tuesday lab, we will do rectifier circuits, we'll do clippers and clampers. So morning section, I was able to at least get through all of the rectifier circuits explanations. Okay, so half-wave rectifier. We will use the ideal diode model to perform these analyses. Okay, ideal diode model. Again, this is a qualitative explanation analysis, okay, lower level explanation, so to speak. But this is the first step in understanding, in your understanding as an engineer. So in an ideal diode model, we only have two states to worry about. Either the diode is off or it's on. Okay. So when I was saying put a pin into the semiconductor physics of things, don't worry about, if it's on, or what are the electrons in the holes doing? If it's off, what are the charge carriers doing? Let's push it to the side for now. You simply analyze by understanding that if the anode has a higher voltage than the cathode, the diode is on. If the anode is at a lower voltage than the cathode, the diode is off. So when we analyze this circuit, remember when we began ideal diode analysis, I stated all we need to know is which end of the diode is higher than the other. And then we simply proclaim that the diode is on or it's off. And then if it's on, then we replace it with a short circuit And if it's off, we replace it with a open circuit. And this is the technique we will use to analyze these circuits. We are not worried about the voltage that is required to turn the diode on, meaning we are not using the constant voltage drop model, no loss in signal, 0.6 volts or 0.7 volts, nothing like that. It's either a short circuit or an open circuit. And that's it. That's what we are doing. Okay. So let's look at this circuit right here. One diode, one resistor. You're applying an AC sine wave to this circuit. So in the positive half cycle, what do we have? You got plus here, minus here. What happens to this diode when you apply a positive signal to the anode and a negative to the cathode? It's on, so it's a short. D1 is on. So positive half cycle, D1 is on. It behaves like a short circuit. It allows the current to pass through to the output resistor. If you apply 1 volt, you're going to get 1 volt. If you apply 1.1, you get 1.1, 1.2, 1.2, and so on and so forth. So you're applying an AC signal to the input, meaning the positive half cycle. We'd expect to receive that at the output. So D1 is on. Let me just say on right there. Okay. Positive half cycle, the diode is on. And so whatever we apply at the input is received at the output. So far, so good, right? Negative half cycle. And I will represent this like this. You can represent it two ways. You can either flip the power supply, or you can keep the terminals same and say you're applying a negative voltage. Either ways. I like to flip it, so it makes it easier. D1 is now off. Open circuit. And nothing reaches the output. Output goes to 0. Okay, output goes to 0. So in the negative half cycle, D1 is off. Okay. And that's it. That is a half-wave rectifier. Okay, let's take a pause. Think over it. Let me know if you have any questions. Exactly 10. And then 8 more online. All right, any questions? Does this make sense? Right? Positive half cycle, diode is on. Negative half cycle, diode is off. That's it. Right? As a circuit designer, if you go to work as a circuit designer, this is the first step you would take. Okay, whether you're a circuit designer or you're performing any sort of analysis. Okay, this is the first step. If we cannot understand what this diode in the circuit is doing, then we would not be able to go in depth. Right? Does that make sense to everyone? Right? And so that's why I always tell students, keep the device physics on the side while we try to understand the circuit workings. And once we understand the circuit workings, then we can go in depth if we need. Okay. So in this case, the word rectify, by its very definition, simply means that there was something that was wrong or there was a problem and we tried to solve it, right? Rectify. In this case, it's not a problem as much as we are simply converting an AC signal to DC. is simply that DC was the preferred choice to run, many of our devices. And so they said, okay, AC is being rectified to DC, hence the term rectifier. And we're using the diode, so diode rectifier. And we're only using half the AC input waveform, hence half wave rectifier. Okay, so that comes from the fact that only half of this waveform is being rectified. And so the waveform that we obtain looks like this. 2 peaks and a trough of 0. Make sense? Now, the question would be, isn't it still time varying? How is this DC? And you'd be correct. It's not fully DC, but it's at least moving only in the positive direction. And also, this is just the first step in creating a DC power supply, right? One of the most important of the next steps would be to apply a component that would actually create a flat line. Before we do that, I can point out that any waveform can be said to have a DC value. So in this case, if you have a waveform that is like this, 0 all the way through here, think of these as, let's say, mountains of dirt, and you flatten them out. Okay, so somewhere around here. And so this would be the average value, or average DC value of the waveform. For a half-wave rectifier, of course, there's a lot of loss. We're not using the full sine wave or the full AC waveform. And so the average value is very, very low. Okay. But again, this was the first step in trying to create a AC to DC rectifier. Now, let's take a pause. Let me know if you have any questions. Does it make sense? Okay. So back in the day, this is how we used to create our power supplies. We'd have a transformer. The transformer would step the voltage down from the power outlets to our desired value. And this is also what we'll be using in the lab next week. So we used to have function generators. You would generate a AC signal sine wave using the function generator applied to our circuit for a nice clean waveform. But now instruments don't have floating grounds anymore. They're all grounded. And so if they're grounded inside, if we apply and we connect an oscilloscope across the output, the bottom end would be grounded. So we can't actually see the actual waveform because it would short out one of the diodes. So we've gone back to how we used to do things back in my day. We are going to use actual transformers to step the voltage down from the power outlet to 12 volts AC. Okay, we'll step it down to 12 volts AC. That's the transformer we're going to use in the lab. Okay, when I first started as a graduate student at Louisville, used to teach this class of, like semiconductor devices. And we had these big transformers with like multiple, bare openings. And you could choose which voltage you wanted to use. And so it was always a fun time because we'd see a lot of sparks flying out every once in a while. But, again, that's how we used to do back in the day. Not like that anymore. So we have a transformer. Again, the goal is to create a power supply, right? So you plug this into the power outlet. The input is the power outlet. No matter where you are in the world, it steps it down to a usable voltage level. And then you connect it to your rectifier circuit, half-wave rectifier circuit. And the disadvantage of the half-wave rectifier is then corrected with a center tap full wave. And we'll talk about the filter in this center tap waveform. Center tap rectifier. So if we wish to use the full AC signal, at a minimum, we need 2 diodes, one for each direction, and we need a specialized transformer known as a center tapped transformer. All this is doing is that we are tapping into the secondary coil and approximately right in the center. So we have equal halves of the voltage on the secondary side. And the way it would work is like this. And I'm going to draw slightly. So I'm drawing a simplified version of the same circuit. Makes it a little bit easier to understand. It's the same circuit. There's no difference. These ground symbols, of course, mean that all of these are connected together, right? So all I'm doing is I'm putting it in the center. This is the easiest way to draw this out. Now, center tap, and I know for a fact that students have studied transformers in 212 magnetic circuits, right? Primary coil and the secondary coil is linked together, and the magnetic fields are interlinked, which causes a voltage to appear on the secondary side because of an input on the primary side, right? This is also the operating principle of your wireless charger. Like wireless chargers have a coil in the charging pad. You put your phone down on top of the pad. Your phone has a coil in the back. Magnetic fields of the coils link up, and energy is transferred from the charging mat to your smartphone, your wireless device. Okay, so center tap transformers. The tapping simply allows us to choose a voltage at a desired level. Center tap meaning approximately in the center of the secondary coil, so it's equal halves of the secondary coil. So if we wish to have a voltage of 12 volts at the output, then we need to have a 24-volt transformer tapped in the center, so each half would give us 12 volts. Does that make sense? Right? In a half-wave rectifier, if you wish 12 volts, then you simply use a transformer, secondary coil, you get 12 volts at the output. In a center tap, you'd have to double that. So you get 24 volts, and then each half is about 12. Also, a real-life example, when I was a student more than 30 years ago, I used to have like a variable power supply. So it had a transformer that had multiple taps in the secondary. And there was a manual switch I could rotate to choose which winding I wish to use. So the winding outputs were like 1.5 volts, 3 volts, 6 volts, 9, 12, and 15. So all of those are simply tappings in the secondary coil. So not center tapped, right? Obviously not center tapped because you're stepping the voltage down from 220 volts all the way down to like 15, 12, and 1.5 volts. 220 volts because I was in India. So tapping does not simply mean center tap. That's the point I was trying to make. Anyway, so let's look at how these diodes would work. In the positive half cycle, you have plus at the top, minus at the bottom. Which diode is on and which one is off? Anyone? Yep. D1 is on and D2 is off. The circuit looks like this. D1 on, D2 off. And the current actually flows in this direction, causing a voltage drop across the resistor. Point of entry is always plus, so plus on the right, minus on the left. So D1 on is replaced with a short circuit, D2 off, open circuit. Yes. So question being asked is, why is D2 off? We are applying a negative voltage to the anode. So the cathode is actually higher than the anode. So here, this is plus, this is minus. And so the diode is actually reverse bias. A positive voltage is being applied to the N-type material. So the diode D2 is reverse bias, D1 is forward bias, it's on, and D2 is reverse bias, so it's off. Does that answer the question? Okay. All right, any other questions? In the negative half cycle, the exact opposite happens. Now, the polarity is flipped. You got a minus at the top, plus at the bottom, minus, plus. And so if you have plus at the bottom, diode D2 is now on, replaced with a short circuit. And D1 is off. Actually, I should have left more space here. Okay, so this is the negative half. So D1 is off and D2 is on. And in this case also, the current is actually flowing in that same direction, causing a voltage drop again, plus at the left, sorry, plus at the right, minus on the left. So the current is flowing through the resistor in the exact same direction for both half cycles. And hence, both half cycles are rectified in the same direction, which would be, if I can draw this out correctly, or not correctly, draw this out without got the mark. Okay. So here it's D1, here it's D2, here it's D1 again. And so both halves are now rectified. So you have full wave rectification. Okay, full wave rectification. All right, let's take a pause while you write it down. Think of it. Let me know if you have any questions. Does it make sense? Yes. That comes later, afterward. So after rectification, that's on top of the rectification. So the question being asked is about the capacitor and the filtering, and so that comes afterwards. Yeah. But the rectifier as it is, just with 2 diodes, this is the output we would obtain. Just 2 peaks. And now, because we're rectifying both halves, the average value of the waveform has risen. It's now doubled, right? Compared to half-wave rectification. But does the ideal diode model make sense? Right? We are not even considering the constant voltage drop. We are not even saying that it requires 0.6 volts to turn on. Positive half, meaning even like 0.001 volt, the diode is on. That's what we are saying. So far, so good. By the way, do you all have any midterms today in other classes? I know several students had a midterm yesterday. How did that go? I don't know if that's sarcasm or okay. What class was it? Oh, stat 350. Okay. Yeah, that's what I think the students told me. Stats or something. Yeah. There was intense studying going on. Okay. All right. So let's talk about the capacitor. So obviously the question again is, how can we consider this as DC, right? So I always like to use, I say it's somewhere between AC and DC. I like to use the term just for myself as pseudo DC, but it's actually going in the same positive direction, even though it's a time varying waveform, same positive direction. So now comes the application of the capacitor. If we attach a capacitor in parallel to our output load, meaning across the resistor, as shown here, right? It'll be something like this. Filter capacitor in parallel with the output resistor, okay? Now think of what the capacitor does. Capacitor is an energy storage device, right? It receives energy from the circuit and releases it back into the circuit at a later point in time. But that energy transfer does not take place instantaneously, right? Thanos could have all the infinity stones. He could snap his fingers all he wants. Energy does not get released instantly. And that is where this is used in rectifier circuits. When you attach a capacitor to the output of the resistor, in the positive half cycle, the capacitor starts charging. Okay. When it starts charging, it acquires energy at its own pace. Sorry. Now, if you make the size of the capacitor large enough compared to the time period of the waveform, meaning the size of the bucket is huge, it's completely filled with water, and you poke a small, tiny hole in the bottom, it will take a very long time for the water to drain out. So the capacitor is large enough, it'll start discharging when the cycle goes negative. But when it begins discharging here, if you let it go, it'll discharge at some point in the future. But before it can discharge anywhere below like 90%, the next positive half cycle arrives, and instead of discharging, it starts charging again. Does that make sense? Right? The size of the capacitor is large, so once it reaches full charge, it starts discharging, but because of the large time constant, it cannot and depending on the size that you choose, let's say, large enough capacitor, probably not even discharges 90% of its stored value. It'll start charging again because the next positive cycle has already hit it. And so discharging, but then it starts charging again, starts discharging, next cycle hits, starts charging again, and so the cycle continues. And so now what we have done is we have taken the output waveform and reduced its peak to like millivolts. Okay, so this is known as the ripple because it's like ripples of waves. Okay, this is known as the ripple, and the output is almost like a flat line with some ripples at the top. because it looks like the surface of the ocean, almost flat if you're looking at it from far away, but there'll be tiny waves or ripples of waves. And so that's what it's called, the ripple or the AC ripple. So if I was to draw the waveform right below this one, it would look like this. Compared to my ground or zero line, it charges, then it begins its slow discharge, charges again, slow discharge, charges again. And this is an exaggerated waveform, right? You could have 12 volts of output and your ripple would be like less than 100 millivolts. So like 0.1 volt. So 12 volts output and the ripple of only 0.1 volt. It's going to be almost like a flat line. So a capacitor has now filtered out the output. And hence, this is also known as filtering. And the capacitor is also referred to as the filter capacitor. Okay, because it's filtering out the AC ripple from the waveform. Your average DC value of the waveform would be somewhere here. Yeah. And again, this is something we'll look at next week, mathematical equations. But does this make sense? Let's take a pause, think over that. Let me know if you have questions. Filtering can be applied to any rectifier. Half wave, full wave, bridge, any rectifier. Yes. So, well, the time constant would depend on the frequency of the waveform. If you're talking about 60 hertz or 50 or 60 hertz waveform, around the world, I've seen capacitors as large as 10,000 microfarads. So 10,000 microfarads is something that I've actually seen in those power supplies. That's a huge capacitor. It's like this kind of cylinder. It's about 10,000 microfarads is what, 10 millifarads or 0.01 farads, right? That's a large capacitance. The ones that we use in the lab are not as big, but I'm already planning to get some from my some of my own parts just to see. So in the lab, we used to, as I stated earlier, we used to have the function generators and floating ground oscilloscopes. We would be able to see both positive and negative half cycles. And then we'd be able to see the filtering action and everything. But with the grounded oscilloscopes, we can't just use a function generator. So we're now using transformers. So you'll be able to see those waveforms. Okay, any questions? Everybody understood everything? Okay. All right, the center tap, of course, is a downside that you need a specialized transformer for that. And so we use what is by far the most common rectifier circuit, known as the bridge rectifier. This is a full wave bridge rectifier circuit. And before you begin drawing, let me show you something. The best way to draw this is to create a diamond shape, 4 dots arranged in a diamond shape. Okay. Then take these 4 dots and you draw 2 diodes pointing up and 2 diodes pointing down. So take the 2 dots at the top and you draw a diode pointing up. In parallel to it, you draw another diode pointing up. And the other 2 dots, you want to draw 2 diodes pointing down. Okay. So draw 4 dots, then draw 2 diodes pointing up and then 2 diodes pointing down. And then take 5 seconds and look at those 4 diodes. What do you notice about the terminals, cathodes and anodes? So there are 4 nodes in that circuit and that configuration. 2 of the nodes, you have 2 anodes meeting, right? So you have 2 anodes at one node and you have 2 cathodes at one node. These nodes are where you would take your output from. So I have 2 anodes on the left and 2 anodes on the right. I mean, 2 cathodes on the right. The nodes where the 2 similar terminals are together, connected together, is where you would take your output from. If you don't have these on opposite sides, then your circuit is incorrect. Okay, so that's something to keep in mind. That's where you would connect your output. And the 2 dissimilar nodes, meaning where the anode and the cathodes are connected, that's where you would apply your input. And so you would apply your input right here. And I'll still stick with the transformer. Okay. And then D1, D2, D3, and D4. Make sense? Okay. So far, so good. Then let's take a look at the positive half cycle. Don't draw this out, not yet. So you have, let's say here, and actually. Okay. That's no standard tap, just a bridge rectifier. So positive half cycle, this is plus, this is minus. Okay. So, and I'll draw this here. So plus on the left, plus here, and minus here, and minus here. Which diodes are on and which are off? D1, on or off? D1 is off. How about D2? On. So replace this with an open circuit. Replace this with a short circuit. How about D3? I heard 1 off. Does everyone agree? Usually that would be the case in a bridge rectifier. The parallel diodes will be on and off at the same time. And then this will be on. And then you have a resistor, the load resistor in the center. And then finally, of course, let me make that input connections. Okay. All right. So positive half cycle. D1 and D3 are both off. D2 and D4 are both on. And the current is actually flowing in this direction. So it goes here, here, through D4 and back to the closed loop. Point of entry through the resistor is from the right. And so it causes a voltage drop, plus minus, plus to the right and minus to the left. And that's just the positive half cycle. Does that make sense to everyone? Let me know if you have any questions. Again, D2 and D4 are on because the anodes are held at a higher potential than the cathodes. Ideal diode model. Again, no voltage drop required. Any questions? Okay. Negative half, the exact opposite happens. We now have, make this easier. D2 and D4 are now off, and D1 and D3 are now on. And the current flows. Actually, I need to change the signs, but hold on. Flows in this direction. And okay. Negative half cycle, source is flipped, positive at the bottom from the transformer, negative at the top. So now the diodes D3 and D1 are forward bias. And so D3 and D1 are on, D2 and D4 are off. Replace with a short circuit and open circuit. Current flows from the transformer in the exact same direction through that resistor from the left. Yeah. And then goes through the resistor. And then thus causing a voltage drop with a plus on the right and minus left. Here. Same direction of current flow through that load resistor results in rectification of AC to DC in the same positive direction. And so we obtain, again, for the second half cycle, negative half cycle also as D1 and, in the same direction, D1 and D3 are on. Okay, so it results in positive rectification for both half cycles. But 2 diodes are required for each half cycle to complete that circuit. So you had a positive half cycle, negative half cycle. Positive half cycle comes out as it is. Negative half cycle, current flows in the same direction, and hence again current is positive, or the voltage waveform is positive to that resistor. So you have a full wave rectification without needing a center tap transformer. And this is by far the most popular configuration. The bridge rectifier configuration is by far the most popular one. Okay. So D1 and D3 are on, D2 and D4 are off. All right, questions? Any questions at all? Does this make sense? Yes, no questions? No. Okay, we'll end class here today, and I'll see you all on Monday. Quiz as usual, and the material will be from the topics we have covered this week. Okay, so that's always the pattern. Quiz on Monday, and covers the material that we learned previous Monday through Friday. Bid you all a good weekend. I'll see you on Monday.